Hi guys, it's me, Sam McDonald, and as you can see, as usual I don't know how many videos I did this for, I'm still in school as usual. I don't know how you've seen all this before. I have Mr. Brown again.
Hi everybody, welcome to my office.
Yep.
So Sam is going to ask me some questions about a couple of things, urban heat island effect and the mountain climate.
Yep. And as you can see right here are the questions. I don't even see them that well, but okay. Alright, so let's start the questions. Move this out of the way. Alright. First question you guys can see is, what is the urban heat island effect?
What is the urban heat island effect? Well,
Yes.
I have a visual here, Sam, I don't know if you can catch that. But the urban heat island effect is, cities basically trap heat. They're heat seas. Why? Well, for a couple of reasons. First of all, they have darker surfaces. So darker surfaces absorb more sunlight and more heat. So also much less vegetation to kind of dissipate the heat, giving up heat through, say, evaporation and evapotranspiration. And also just very secondarily, the heat generated by like pedestrians and cars and that kind of thing. So the second question is,
Oh, yeah. Second question, as you guys can see on the paper, is what is the urban? How is the urban heat island effect contributing to the climate change?
okay, well, it's driving up. Well, it's not the principal driver of global temperature, but it does contribute to the overall warming, but in a different way. Not through greenhouse gas forcing so much, though a lot of greenhouse gases are emitted by cities, but just by being what we call a warm city.
Yep.
So all the processes I just described, a darker surface field with less vegetation, and therefore acting more as a heat sink. And then have enough cities that are warmer that will contribute to the rise in temperature.
Alright. Third and final question, as you guys can see, is why does the temperature turn colder with altitude in the mountains? What is unique about the mountain climate?
Okay, I have a visual. If I can find a picture of the top here, that'll be a second now. Well, I apologize, audience. Let's see. I'm going to have to go back and get that image. Superforce our discussion in astronomy. All right. This is the appropriate one. All right, so why does the temperature change with elevation, say, in the case of the mountain? Because it does it everywhere in the atmosphere, but it's most felt experienced around mountains because we climb mountains. But basically the change in temperature is 6.5 degrees Celsius for every 1,000 meters. And why? Because you're moving away from the Earth's surface, which is warmer,
Yeah.
like moving away from the radiator, but also because the atmosphere gets thinner, so less effective at storing heat. So the Earth radiates heat back to space in the form of infrared radiation. So by the time infrared radiation gets to certain altitudes, like 2,000, 3,000 meters, it's lost a certain amount of heat. And secondly, well, you can see those mountain tops as a result, snow caps, so obviously it's colder, snowier can be mountains in high latitude. And also, mountains can cause what process or phenomenon we refer to as orographic lift. So sometimes in a moist air mass, air can get lifted over a mountain, form clouds, and result in rain showers. So the mountains, in that sense, are like a sponge. They squeeze, moisturize the atmosphere. So something called a mountain shadow. So by the time the air gets to the other side, it's all dry. So all the moisture has been wrung out. So oftentimes on the wind side of mountains, the climate tends to be drier. If you look over here at this map, this lighter hue represents a drier climate, less precipitation, in order of maybe 20 inches or less per year. In fact, these climates, the Rockies, are semi-arid. In the case of like Denver, for example, it's a semi-arid steppe.
All right. So some of my viewers have some questions off of Google Plus that I remember, and they had 2 questions. So you mind if we do those?
Sure.
All right. Why is the desert hotter than most places on Earth?
Why is the desert hotter?
Yeah, like hotter than most places.
My mini model of the Earth is deserts. Depends on, not all deserts are hot. For example, Antarctica, bottom of the Earth here, is essentially a desert by definition. It's a very, very cold desert. The hot deserts tend to be located toward the equator in the subtropics. And there's a reason for that. The air, around 30 degrees north, tends to sink. And when the air sinks, it compresses, and in obedience to the gas laws, it heats up on diabatic compression. So the air warms and also becomes much drier. So also, as the reasons I described, deserts can also form in the lee of mountains and have a drying effect. But in the case of like North Africa, the Sahara Desert is right around 30 degrees north. So the air in this location tends to sink, and you have this tremendous content of land mass that's capable of much more effective at absorbing heat than, say, the ocean.
Right. And why is it windier as you move closer and closer to the ocean?
Windier?
Yeah.
Well, because there's less friction, less, like, for example, skyscrapers and hills and mountains and things that might divert or barricade the wind. So just simply because that environment is much more open, there's nothing really to stop the wind.
Alright, so what is the difference convergent and divergent boundaries of currents? That someone else asked.
Convergent, you mean plate tectonics?
Yeah, does it have anything to do with the climate change? And what's the difference between divergent and convergent?
Visual. Okay, so the Earth here heats up. So inner core, outer core, and the mantle. So that drives heat. So the hottest place is supposed to be the inner core, next to the outer core. And that drives heat or convective currents. So in the case of, say, the Mid-Atlantic Ridge, the heat is rising, like, you might think of, crude analogy, but like steam from a tea kettle. So that is pushing or diverging the plates in opposite directions. So pushing the plates this way. So this slab of crust has to have somewhere to go. So it bumps into this continent next door, and it gets pushed underneath because it's more dense than the wider continental material, so it sinks. So that would be a convergent zone. So we have this running down the middle of the Atlantic, called the Mid-Atlantic Ridge Rift System. And a really great example of this is also called the subduction zone. It would be around in the western Pacific, sinking Japan. The Pacific plate is sinking into Eurasia.
Alright, so, and a few other questions were, why is the country warmer than the Arctic, and why would the colder in the mountains be colder than the country?
Could you ask that again, please?
Alright, so why is the country warmer than the Arctic and the mountains?
Country? What country?
Like, doesn't really matter, like, any, like,
Depends on which country.
well, a lot of people ask me Florida and Germany, like, in the United States and, like, Germany.
So if we look at the curve of the Earth, right, facing the sun, the most direct rays, because of that curve, will strike near the equator. And then the curve tends to move away, so the rays from the sun tend to get weaker as you move along this curve toward the poles.
Alright,
So, in other words, the mid-latitudes, the subtropical zone in the equator tend to receive the most direct sunlight.
alright. And why are the Arctic and the mountains colder than the country, like Germany and Florida? Or Florida state, but...
Why is the Arctic colder?
Yeah.
Well, for basically the same reason. The curve moves away from the sunlight. And also it has to do with the tilt of the Earth as well. So there are times, for example, like during Northern Hemisphere winter, when there's no sunlight at all reaches the Arctic. And it's very, very cold.
Alright. So are the mountains technically colder, or do they warm up over time sometimes?
Well, overall, it has to be related to the overall climate regime of the planet, but mountains, regardless, as I pointed out, tend to, as you go up in altitude, the atmosphere becomes colder.
Alright. So enough video here. Alright. Alright, bye guys. This has been Sam McDonald with the climate change and all the explanations I forgot to put in the last video. This has been Sam McDonald with...
Oh, you want me?
Yeah, they have...
Oh, Mr. Byrne. Thank you, Sam. It's been a pleasure.
Yep.
One of our Ask Mr. Byrne sessions, right?
Yep.
So see you folks the next time.
Alright, and I will see you guys next video. Please like, comment, and subscribe. Alright, bye guys.